Go ahead.
Okay, thanks. Okay, maybe before we start the sessions, are there some questions or some remarks? So we have this Slack channel open. So if you have anything, just write it there. And I try to see it. Otherwise, I guess Simone or Stanius, Christos will read it. Okay, so we just had in the session before noon, we just discussed how to parallelize for loops with OpenMP. Basically, yeah, you have to, if you want to reduce something, you can add this with a loss course. Now in this session, we will discuss tasking. So this allows you to identify tasks within the parallel region. Basically, this should simplify your parallelization of the code. I mean, if you have complicated structures, so if your computations are not clearly located in for loops and maybe are distributed in your code, then this is maybe better for your implementation. So you can identify tasks in parallel regions, which are then picked up by threads. Yeah, we will discuss this in detail in the upcoming hour. Okay, so the task directive. So you can basically in parallel regions you can declare critical regions, as you see here, where each thread has to run through this region, but after each other. So first threads which enters this region will start it, and the other threads will wait for it, and then the other threads will also run it, but one at a time. So this, in principle, makes the critical region makes your code again serial, and so it's clear that if you declare this, that the runtime scales with the number of threads. So if you have more threads, and each of the threads has to go through this critical region, the runtime just increase. So more you can inside of parallel regions you can. This is the first point here. Inside of parallel regions you can declare single regions. Just here with this OMP single, and this is just run by one thread. Yeah. Tasks define a block of code, a task to be run by a single thread. So you can, inside the single thread, you can define tasks by which is then run, which is executed by one thread. So for example, I mean, just by writing this pragma OMP task, and then the stuff which is one task. So example code would look like this. So maybe you have a parallel region, then you in the parallel region you open a single region, and within the single region you you have several work to do which you want to assign to different threads. So in principle, what the program would do here, it would enter the parallel region, then the single region, and then you the first thread which arrives at this task will be assigned to this task, and then the program in principle will run through, and then the next thread which arrives here will be assigned to this, while the others are just running through. So you can identify easily. You can distribute work easily by identifying regions which are can be done by one threads. maybe this becomes more clear if we really do an exercise on this, how this is working. For this, there's exercise 5. So again, log into the machine and copy exercise 5. So I will do it also to your home directory or to the directory where you're currently working in. So let's do this. Did I copy it? Okay, let's take a look how this code looks like. It's just a code which we already had at the beginning in the introductory session. We open a parallel region here. We get the number of threads and the ID of the threads, and we print this out. Yeah. And then you see in principle that each of the threads say hi again. So let's do this. I think we already did things. I mean, we did this already, but then we will go on the next slide. We will go to assign tasks. Submitting and take a look what the route. Yes. Shouldn't forget the basics. Compile it and submit it. I think okay, the error is already overwritten, but okay, probably you would see an error that executable will be not found if you don't compile it. So now I was a bit too fast, but I was too fast, but then yeah. Okay, so you see again what we saw at the beginning of the first exercise. Now let's go to add a single region to this to see what the single region is doing. So. Okay, they're still joining. And as you remember, I already discussed what the single regions is doing. Let's take a look what if you compile it and execute it, what happens then? So what happens is that a single region is only executed by one of the thread. So if you declare a single region, usually here you declare a parallel region, so all the 5 threads which will run through it. And then if you declare a single region, only one of the threads will do this work. In this case, the number 2 was doing it. So the number 2 was arriving as was taking this this work, but it's really it's randomized who arrives first there. So it's not always thread 2. It's sometimes, I mean, you see, it's just who arrives there first and will run through it first. Here it was thread 3 and so on. So you don't have a control on which thread it will take this. This was thread 1. Okay, so as shown here in the slide. Now we already discussed this. We can now assign tasks to the different. I mean, you can inside a single region we can assign tasks. Let's try this out. So we just have two messages, two tasks with the same message, only that we identify the first task with message 1 and the second task with message 2. And let's see what the program is doing. Okay, the code looks not really nice. Okay, so inside the single region, we defined two tasks by pragma OpenMP task. Let's compile this and run for a few times. So in this case, thread 2 arrived, got assigned to the first task, and thread 3 was assigned to the second task. And both, I mean, the printout of the first task was faster than the second task. However, this is not always the case. So, for example, here now, the task, I mean, the second task was just faster than the first task, printed out faster, printed out this message was printed out faster. So if you assign tasks, this will be picked up by one thread, and this thread will run through it until the end. And how fast this gets executed, it depends a bit on how the machine is working on this. So if you define different tasks, that doesn't mean that the tasks are performed after each other. So they just get the threads, one of the threads get it and run through it. But how fast they are, if the first task is executed earlier than the second task, it's just to the moment of the machine. Okay. So here some output of this. So you see that sometimes the first message is faster, sometimes the second message is faster. You can actually, there are commands which, I mean, it's just task wait, which forces the program to wait until the previous tasks are done. So if you, for example, if you add between the two tasks a task wait, this will wait until all of the tasks before this are finished, and then you would see these two messages after each other. So let's try this out. Okay. Now the second is in the second position. Let's take a look if this is really the case. It seems so, yeah. Okay, so you can actually, if you have some, I mean, if you have a task which depends on something what was done before, you can force all that this task is will be executed after the first one is was finished. Oh, it's finished. Okay. Okay, let's take another example with respect to that. So in this case, it's exercise 6. Yeah, by the way, if you have any questions, also just raise your hands and write it in the chat. I don't want it to be too fast. No? Or if you need more time, let's say. Okay, I guess this exercise is in the line of the first exercise. Only that it has some more tasks. So let's copy it and let's take a look what this exercise is doing actually. Okay, so you in this case it's not printing out the thread ID, is just counting from 1 to 3 in a OMP in a single region. Yeah. Okay, if you compile this, what the submit file looks like. Okay. Yeah, what you see, yeah. So in the single region again, you see that what actually I don't really specify here the number of threads. So in principle, 40 threads will run here, but because it's in a single region, only one thread will execute it, and you see in this case, it's in order. So it's correctly counting from 1 to 3. So if we now add tasks like this, so we can task. Then let's see what actually happens. We have to recompile it. Submit it and taking a look. Let's do it again. It's still in order. Looks fine. Okay, somehow this is always in order. But in principle, it should be taken up by different threads. So the printout, okay, I guess because of the 40 threads, it took a while. Not sure if there was an overlap, overhead if I shrink the number of threads to a number of 3, as I did here, then actually it seems that this overhead is gone, and I get sometimes the 1 is the last, sometimes the 3 is the first, and so on. So you don't have it in order. So with task wait, you can infer that you can ensure that 1 is coming first and 2 is second, and so on. Or if you increase the number of threads. But okay, this is just by luck. Okay, so if we want to add an additional task to print done at the end, what we have to ensure doing this. Maybe you can do this, check this out. If you're able to add a printout at the end, which is always at the end. Maybe give you some time to do this. Okay. Yeah, I mean, we already saw this in the previous exercise by adding a task wait to the code and then print out done. So let's do this. So just assigning again a task and then print done. We compile and submit. And then you see, as we already said, this task wait is waiting that these 3 tasks before are executed, and then it goes to the next task, which is here the printout of done. But how they are, in which order they get executed, it's not. Task wait doesn't care about this, so it's just waiting until all tasks are finished, and then it goes further. Yeah. Okay, so for the next exercise, we have another example for tasking. In this case, yeah, let's go to it. If there's no questions or no remark. Okay, again, copying the exercise. Okay, this one is, I mean, in this case, it would be nice if you can, I mean, we go now through the code, explaining the code, what the code is doing, and then you can try to parallelize it with the commands we learned. So in principle, the code consists of you know, of the main region, and then it's called here it's called this functional process. So let's go through the lines that you understand it, and then at the end, what would be nice if you can take a look, try to speed up the while loop here. Okay, so you create an array of n integers, and you fill up. I mean, this code fills up this array n of n-1 of these integers of the array will be filled up by random numbers, while the last entry of this array is assigned to -1. And then, in principle, the work which is done in this program is happening in the while loop. So you have, in principle, a pointer, which is pointing here to the first element of the array. This pointer you give to this function process. And if the function process finished, you increment this pointer by +1, and you call again the function process until the value of the function the value of the where the pointer is pointing to is not any more larger than 0. And this is the case if you reach the end of the pointer. Okay, so basically, okay, you can go. What the process is actually doing is, you see, you sum up in principle a variable. I mean, you see, you give the pointer to the east element of A, and then you take this value and you sum. I mean, you sum from 1 to this number. You sum all values up. So 1 + 2 + 3 + 5 + 4 until the element of which you got here from this function, which gives you an integer random number which is larger than 0 or larger or equal to 0. Okay, the question is if I mean, if you now think about how to parallelize this, okay, basically you can basically you can this process can be called by each thread individually. You only have to be careful because yeah, the pointer is increased. It's critical, otherwise the while loop will run forever. So maybe some basics. The program uses in the moment an array of length 10, and it takes around cyclone in the CPU around 1 second to complete. So the goal of this exercise would be to use OpenTask derivatives to distribute the work and to speed up this loop. So basically, you can use OpenMP single to define a parallel region, and I mean OMP parallel to open a parallel region, and then OMP single to define a scalar region. Then you can use OMP task to specify a block which you want to distribute to the different threads. However, there's something, I mean, we already pointed it out, but you have to define, you have to be careful, you have to use a first private at some point. And be careful if you can end up in an infinite loop if you do something wrong. So I think if you have questions, I mean, I give you some maybe 10 minutes to take a look to it. Try to use OpenMP task to speed this up, and then we discuss the solution. And clear, if anyone has questions, please raise your hand, open your microphone also, and ask. Yeah, I mean, if I can also give some hint, or is this, or does it already work for someone? So the idea is to open a parallel region before this while loop, and then define a task within the while loop. And one has to be careful that one don't do anything wrong with a, pointer. Okay, maybe we can do the steps together. So okay, so the while loop itself should be a parallel region. And then this region should be executed by a single processor, so OpenMP single. And then one has to be careful with the pointer, as I already mentioned. So the process itself is the task. So and to protect the pointer, one can use here a clause first private. Of the pointer. So basically, what is now? Oh yeah, there's a problem. So basically, what is now? What is happening now? You open. It could be much more pretty, but we open here a parallel region. Then we say this is only executed by one thread, and then we assigned here in the while task. So the first element of the first element of the array is larger than 0. So this will then the process will be called. So one thread gets this task, and then the while loop goes one increments this pointer one further. We will check if this element is still larger than 0. If it's, then another task will be assigned, and so on. And going out of it, that you make sure that the pointer is not initialized again before you go into the process by assigning it to the first private. Okay, let's compile it and see what it's. Okay, what you see is now that we didn't check the runtime actually in the non-parallelized version, but here the runtime is 0.2 seconds. So let's check if it's really gets speeded up. Threads. Go to N. Done. And you see that it starts with 1 second, which was running with one thread, and then increasing the number of threads. Actually, you see some speed up until a certain number where you don't see any more speed up. I mean, obviously, the array has 10 elements, and because this means that the while loop goes only over 10 elements, or in this case, only 9. So you cannot beyond this, there's not a speed up. So if you increase now the length of the array to 40, we hopefully see a speed up. Okay. Okay, we discussed this, I guess. Okay, let's go to another example. In this case, computing Fibonacci's numbers. Here we will see that OpenMP can produce overheads, and there are clauses to reduce this overheads. Okay, basically, it's a recursive approach to calculate Fibonacci numbers. So you start with the largest one, and then you go recursively down. So you get a tree of function calls. So the idea is here to call the Fibonacci, and then you see you call it with with your, if you have here with the number n, and then you have a recursive function call where you calculate x by calling Fibonacci of n-1 and y by calling Fibonacci of n-2, and then you return the sum of these variables. So you create a lot of work by doing this from the top and not from going from the bottom. Okay, so as we learned, we could just use now tasking to I mean, obviously here we don't have a for loop, so this tasking approach would be the way to go. And the work is done actually here in this function Fibonacci. So we could say, okay, this call here is one task, and this call is another task. Yeah? So we define a parallel region, find in the region a single one, and then we assign one task for the function call Fibonacci n-1 and one task for Fibonacci n-2, and then we wait that before we return x and y. By doing so, actually there you can try this out. There is in the folder where also the other exercises are. There's exercise x_fib. If you do this, and if you parallelize like this, and you increase the number of threads, you see that it seems that you don't really see the speed up. So you actually slow the process down. Just one reason for this is you just create a lot of tasks. If you, I mean, each of these tasks calls fib again if n is bigger than 2, and doing so you create a lot of tasks, and this slows down the program. So there is a possible way to avoid this, and this is the if clause. So if the expression of an if clause on a task is evaluated to false, then the task is suspended. The new task is executed immediately, and the parent task resume when the new task is finished. So if we add this to our function, it looks like this. So you just add an if after your shared x. Then in principle, the task is only created if n is bigger than 30. And this actually helps to speed up your scaling, so you don't create a lot of tasks, and you can basically speed up this recursion. It's still not ideal, so you still can improve this scaling further. Basically, by avoiding that you run into this check, so you just have another if condition, and you call just serial Fibonacci recursive function before you always end up in this pragmas. Okay, this the scaling on Cyclone was not perfect, but it was improving the execution time by 1 magnitude by doing this. Okay, so I think we are now 45 minutes in the session. We can make maybe, I mean, we already did some, but we can make a small break of 5 minutes. I mean, you can think maybe about these questions, and then we will just come to the vectorization as the ending of this introduction to OpenMP.
Okay, thanks, Jakob. We carry on in 5 minutes, as he said.
Okay. Okay. Yeah. I mean, this was a recursive approach to calculate the Fibonacci numbers. You can do it also the other way around, which would be much faster, but for educational purposes, you increase the workload here to show that you actually can speed it up. Okay, so the last chapter is vectorization. Basically, modern CPUs are not anymore. I can do floating point operations on not only on a single data. They can do it on a multiple data array. So there are there are several instruction sets where you can not only do one floating pointing operation per cycle. You can do severals. However, usually you have to implement this using the instructions. However, modern compilers can auto-vectorize your code in order to use the vector. I mean the potential of the cores, the vector units of the cores to speed up your computation. And okay, so to use auto-vectorization of the compiler is basically user-friendly, because you don't have to start to dig into your code and implement all this vectorization intrinsics to your code. So since OpenMP 4.0, there are, in principle, we can put hints into your code that, for example, loops or areas in your code are vectorizable. So not all the auto-vectorization of the compiler cannot catch all different possible vectorizable regions, and so OpenMP gives you some methods to speed up and to tell the compiler, actually this is a loop which you can auto-vectorize. So in principle, this is like before. You just use this. You just indicate a region which is vectorizable with SIMD. So yes. And this is, I mean, vectorization of loops can only be done if the number of iteration steps are known from the beginning, and it's not dynamically changed during the for loop. Okay, so we can take again a look to the exercise 3, where we actually where we which we used for OpenMP parallel 4, and you can check it out what happens if we write their OMP sim. So let's do this. The problem is that not the problem, the good thing is that most of the compilers are already quite good in auto-vectorization, which means that it's difficult for a simple program to show for a simple program that you actually can speed it up. Then maybe we try and see if, I mean, maybe the default compiler is able, we can see something, but okay, we have to try it a bit out. And sometimes it works, sometimes not. Okay, so, and then in principle, I mean, to control the auto-vectorization or the level of the optimization of your controller, you have, of your compiler, you have compiler flags. If you don't indicate them, then you just take the default one. So usually the optimization level is indicated with -0, and then you can add a number from 0 to 3. We can take a look into the manual of the compiler to see actually what kind of optimization levels these are. Okay, if you compile with 0, you don't have any optimization, so you switch off every optimization. Let's take a look what the code is doing then. So I think the numbers we had before, maybe a bit slower even. You see 13 seconds, 0.13 seconds. So if we compile this program now as -01, then we see some speed up just from the just from the optimization and auto vectorization of the compiler. So in this case, you see it goes down to 0.10. Before it was 0.13, and so on. So you can speed this up. That's -02. Maybe it's too simple and you don't see any influence. Yeah. Okay, so there is this flag fast, but this is in principle also -03, so this is aggressive optimization, and if you you have to be careful because some of their you might lost some accuracy. So. Okay. So actually, what you saw, I mean, I add this Pragma OMP SIMD to the loop which I want to vectorize. Yeah, but the speed up doesn't really change from the first loop, so the compiler already can catch. I mean, this loop here can be vectorized, so you can take. I mean, vectorization would be you don't go step. I mean, element by element wise. You just go maybe you take you put 4 elements together, and then you operate on this 4 elements in parallel. So you can actually depending on the CPU, on the generation of the CPU, you can make larger steps. You can have more floating point operations in one circle of your CPU. Okay, so what you see here, if I add a OMP parallel 4 to it, you basically see that that the compiler, the default compiler is the version is too old. So it's a 4.8 compiler, which doesn't have the new additions included. So for that, we can actually, on the machine are different generation of the GNU compiler available. For example, if you just you can load them by module load, and then you have this quite many modules available. What you can do is if you don't want to look through all them, you can just tape DCC, and then with tab you can see all the modules which are starting with GCC. So, for example, you see a GCC 10 if you use tab. So let's take this one and compile again. And now it's compiled because it's already included in this this version. So if you take a look at the version, this is now 10.2. So the CC1 is now 10.2. Although I'm not sure if you see any speed up because this program is quite simple. I would say no. Really, too many things on the same time. I put a parallel region so it's clear that it's faster. Let's do OpenMP number of threads equal to 1. To see if the new compiler already has some influence. And basically not really. So you see that it's 0.1 seconds with a VCC 10. Okay, let's see what happens with 10 threads. You see a speed up, which is not a factor 10, but it's getting better. Okay. Yeah, so as at the beginning, I told you there are some OpenMP environment variables. So one of them is dynamic. I can check out this, for example. This should assign dynamically number of threads to your to special regions. So if you have different regions which are working optimal with different number of threads, you might this can be dynamically changed during the program. So you don't really have to care. Okay, what you see is that this is not working always, but maybe for playing around might be interesting. So the first one is a bit slower now than the last one. Yeah. Okay. Basically, this auto vectorization, there you can also get a report if your instruction was working by, for example, the Intel compiler gives you a report. Things like a compiler, you can also get a report. So let's switch to the ICC compiler, the Intel one. And take a look what kind of if you get some informations if the code was parallelized or not. So basically the change which if you switch to the Intel compiler, you have to change the flag f_openmp to q_openmp, and here in this case, this flag here, this compiler flag minus qop minus report equal to 2 will generate a report about the vectorization of your code, which you also see as a remark here. So you got a file which has the ending opt report. So we can take a look to it. And the two loops, if you look into the code, there are some loops for initialization. You fill up the arrays with random numbers. So our interest would be the for loop. And actually, we see that the first for loop was vectorized. Let's see here. And the second for loop, where we wrote pragma OMP SIMD, is actually vectorized with the help of OpenMP. It's written. I shouldn't move the mouse. It's actually shown here. So it's actually written down. Okay, let's take a look if we see any difference between and Intel. Yes, it's slower. Usually the Intel compiler gives some, but maybe it's depends here a bit on this dynamic. It's number of threads. To 10. Yeah, in this case, you actually see that the auto vectorization helps because the second for loop is a factor 2 faster than the first loop. But in case of the GNU compiler, this was not the case. In the case of the GNU compiler, the version 10 could auto-vectorize the first loop as efficient as the second for loop. So maybe I'll just show again the for loops, how they are now parallelized. So in the first time, I just have parallelization. So because it's quite simple, the compiler can get it that it's able to vectorize. And the second, you indicate with SIMD that this for loop can be is vectorizable. And okay, let me check what is ICC compiler for version. Okay, it's in 91, so it's also relative new. Okay. Other questions? I didn't follow Slack. Yes, I started with this. Sorry, I started. I mean, there's a question. Doesn't need the pragma open parallel from the original X03? Yes. I mean, if you want to parallelize it, yeah. So I wanted to start it with a serial version. So you can also indicate serial code that there are regions which you can vectorize. So it doesn't need to be the parallel region, but you can combine it also. Yeah. Okay. Okay, then you can add more clauses to the SIMD directives. You can actually say, for example, that specific. I mean, here's just a list. You can tell, in principle, the compiler that specific variables are already aligned, so they can be visible used directly for their vector intrinsics. Then there are, I mean, there are directives for if you need to do reductions, which we already had in the parallel 4 directives, and something more like to define private variables, or to basically nested loops are difficult to vectorize for a compiler, and you can put in front of nested loops collapse that out of this nested loops is created one loop that the compiler can auto vectorize it. So moreover, you can declare functions to be vectorizable. So you put this in front of a function. So now we have it in the code, but in front of a function, you can also say, okay, this function actually is valid for vectorization. And there you have also different clauses again, like we had before. You can say actually, okay, this argument of your function is aligned. And there are different options for this. Maybe let's take a look to our final example or exercise to play around a bit with that to see how this works. Yeah. So it's in principle the same function like we had before, only that one of this for loop is sourced out to another file, which is called FNT. So let's take a look to this function. As I said, it's the same principle like before. Maybe this highlighting is better. So you have again the normal for loop to cross-check, and then we have the other for loop, which is sourced out into a function, which is called AXPY, and this function is contained in the function file. As you see, there's just a for loop with a function. Okay, so and what does it mean? We have to we can link. We can create. Oops, we can compile this first, and then we can compile this one by linking the .o file to it. It's known. Let's take a look. Submit. This is submit file. Doing okay. So we see again what we saw before. If we this is a serial version of the code. If we compile it with -0, we don't have any optimization. So if you want to declare now that this function is vectorizable, we can write it in front with pragma declare zimni. Okay, then we have to take it. To increase the vectorization. Let's do. Let's take a look what is coming out. Okay, what I did now is yes, but it's somehow. Let's write an OpenMP here. That seems a bit changed so much. Yeah. So okay, what I did is I compiled the function file now with optimization -01, and the file itself is -0, which means a function in the for loop in the main function was not optimized, while the function in this file was optimized, and you see this in the execution time. So basically, this got optimized, and while this is still not optimized. So when we can now make this even worse. So we can make not worse but faster by using this. At the end, this function structure is still very simple for the compiler. So this SIMD, you see that there's now the speed up even faster. Yes, this is right. So even if I don't declare it, I think what the compiler is doing is compiler compiles different versions of this function with different vectorization levels. And then depending on what kind of, if there comes aligned memory, then it's using the more vectorized function. Let's take a look if this is really the case here, because the main function is now still compiled without optimization. Yeah, this is the case. So you see still the speed up of the second function. However, if you have more complicated functions, so functions call, it might be not really obvious to the compiler that the data which you give is aligned, and then this can help to speed up specific functions just by using auto-vectorization. Okay. I think I'm also at the end of this session. So if there are not specific additional questions, I will just go to my last slides. Okay, so maybe just a recap of the day. We started with an introduction to, we started just with the basics, the syntax of how this looks like, and then OpenMP provides some functions where you can get the ID number of the threads and the total number of the threads. You have to be careful with the data sharing, so you can have clauses for this. You can define you can create a list of private variables, and you can also declare a list of shared variables, which are within a parallel region that will be shared. Then we took a look to how we can share work in case of a for loop construct and in case of tasking. And at the end, I was just trying to show you a bit how OpenMP can help to vectorize your code and speed this code up. In principle, it can help to auto-vectorize your code, can help the compiler to auto-vectorize the code. And for this is SIMD Pragma is available. Okay, so before, this is in principle what we discussed today. So you will find this slide on the GitHub page, but also on the web page, as far as I understood, Stelios. So you can take a look later if you missed something, or you just wanted to recap what we discussed today. Let me conclude to give you some outlook on the next events. I don't know if Stelios wanted to say something about this, but within the this National Competence Center for HPC, we will have additional couple of events in the first half year of 2021. So upcoming is the Industrial Week, which is in the first week of March. Then, as I already said at the beginning of this course, we will have an intermediate training event, which will take place at the third week of April. This in particular will include more advanced topics like MPI, OpenMP we discussed now, but MPI and hybrid programming, also with a more deeper dive into how to use Python for HPC and optimization, profiling of your application, and so on. At the third week of May, we will have a hackathon here where we're still looking for projects, but the call is still not open. But maybe keep this in mind if you have a specific project which you want to enable on our machine, and which might be suitable for this week, where we can help you to put this on the machine and scale it. I think the date 19th is wrong, it's 17th, but all this information is also available. We send around emails quite regularly, so you can subscribe to the mailing list on our webpage. And if you have any questions regarding our program for the support of academia, and also our program with regards to industry, and just write me an email or just let us know. Yeah, so thanks for having you, and hope you see you all at the intermediate training event in April.
Thank you, Jakob, for the final remarks and the summary of the future training events. You saved me from doing it. I would add to what Jakob said, that we have the industry week on the first week of March, so Monday 1st, Tuesday 2nd, and so on. But the first day, Monday 1st, is more of an academic day. It's also an academic day. So as I said earlier, we're going to have a few presentations on what the Competence Center is, which, you know, it's the beginner, it's the introduction, which I sort of gave on Monday. We have, let me find, sorry. We also have details of how to access infrastructure, which is what I gave the other day also. Then Jakob and Kyriakos and Christos and Simona will talk about how the Competence Center can support academic groups in industry. So, you know, user support is when, well, there's different types of user support that the Competence Center offers. There's the user support that George and his team offers, which is the technical aspects of getting started on the machine. So creating your accounts, Linux help, problems with your data, with your workflows, and so on. But more specific user support, which is carried out by our high-level support team, which is Jakob, Kyriakos, Simone. It's specific to your code, so helping you with improving your code, improving your algorithms, improving the scalability of your codes, the efficiency, and so on. So those sessions between 3 and 4 will describe how the high-level support team aims to, well, what it offers to academic groups and to industry. So you might be interested in joining that. Then we will have a session on Monday at 4 o'clock on how collaborations between government, industry, and academia can occur. And this whole week in March aims to encourage collaboration between industry and academia, academic groups and industry, academic groups and government, and so on. So if you are head of a group, or if you want to see what's going on, then please sign up so you can participate in this event. And in the afternoon of that day, so between 5:45 and 6, we have the user forum. And the user forum is basically the users platform, the academic and the industry community platform to tell us what they want from the Competence Center and what kind of support we can provide them. And then the other days are more industry oriented. If you know anybody from industry who might be interested in this event, or any other academic people who might be interested in this event also, because we are trying to network industry and academia between them, then please refer to them to our website. As for yourselves, this was our first training event. I hope you enjoyed it. I have put on Slack a feedback form for the final day. If you can please fill it in. It's similar to previous days. just some general response for Jakob's session, and also some details they can provide us for the whole event as a whole, in general. Next one, as Jakob said, our intermediate, which is a build-up of what you learned in this one, is in, when is it? It's in April. Yes. So you get an email about this when the registration opens. Sign up and become a member of our meetup page, which I believe most of you probably are members, and there you get notifications of our events. We have training events, we have seminars going on, so keep a lookout for the seminar sessions, because there might be a specific subject that may interest you. And again, if you have any questions concerning user supports, whether it is on accessing the system, on developing your code, on Linux stuff, then you can contact me, you can contact Jakob, you can contact our CaSToRC.support@CYI email, or HPC support@CYI, which is George's support email. And always, if you need anything, reach out to us. Okay, you know who we are. You can find our emails on the websites, but CaSToRC.support will find someone to reply to you. Again, please provide us with your feedback on the form that we pasted. The Slack channel is going to stay alive, and people will be monitoring it, so you can always contact us through there as well. So to close off, I would like to thank you all for joining this first event. I hope you enjoyed it. I hope it was helpful for you. The videos and the presentations are all on there. Jakob's are uploading as we speak, and when he sends me them, the presentations, and they'll be made available. Well, all the other videos and all the other presentations are available from the previous days. Jakob's will be linked, well, when we close off. So I'd like to thank you all. If there's anyone who would like to say something, who has a final question on anything, then please unmute and speak now. No. So I'm going to close the whole meeting because I need the video to upload. And I hope to see you all in the next training event in April, and possibly in our future seminars and industry week. So bye everyone, and thanks for joining, and we'll talk again.
Thanks for joining, and yeah.
Thanks a lot.
Bye everyone.
Bye.
Bye.